Chapter 3.10 is a review of how to calculate empirical formulas from laboratory data. Just to review really quickly, what are empirical formulas? Those are just the lowest whole number ratio version of a molecular formula. So for example, this is glucose. If we were talking about lowest whole number ratio, we mean carbon compared to hydrogen compared to oxygen, which if you reduce all of those is CH2O. If we're talking C2H6, that would reduce to CH3. And then oftentimes the molecular formula is already in its lowest whole ratio, so it's going to be N2O3 for this last one. So what this means is you're going to get data, and if you use moles to figure out, how one element compares to another, what you would see with glucose is for every 1 mole of carbon, your data would show that there are 2 moles of hydrogen and 1 mole of oxygen. If you're looking at the next one, for every 1 mole of carbon produced, there would be 3 moles of hydrogen. For every 2 moles of nitrogen, there'd be 3 oxygens. So to put this into actual practice, let's say you were doing a lab, you took a nitrogen oxygen based compound and you decomposed it and you were able to separate the 2 parts. If this is how many grams of nitrogen you were able to collect and this is how many grams of oxygen, if you can figure out how many moles of them you were able to separate, then you can compare them to each other. So we would always start with whatever the gram value is given to you in the question. So we start with 25 or 24.5 and 70. So mass does not end up in the same ratio that you can't really use mass to compare one substance to another, because one atom of nitrogen and 1 atom of oxygen is a 1-to-1 ratio, but because of protons and neutrons, they don't have equal masses. So we need to convert this to moles, because what we're really talking about is the number of atoms, not how much they weigh. But we can use mass to get from the weight that we find in a lab to how many atoms of them were present. So we're going to take the 24.5 grams of nitrogen, divide by the mass on the periodic table, take the 70 grams of oxygen, divide by the mass on the periodic table. And what we find is for every 1.75 moles of nitrogen, there are 4.38 moles of oxygen. So technically, this is already a formula. What we're really saying is this is N 1.75 and O 4.38. Obviously, this is not a correct formula. It's neither whole numbers nor is it the lowest version of what this could be. So we need to be able to manipulate this somehow. The next step is to take these 2 numbers and reduce them down to as low of a whole number as we can get. So we're going to take them and divide by the smallest one, and we get N1O2.5. Okay, so in honors chemistry, pretty much all the questions like this that we did, we ended up with whole numbers. This might be 1 and this might be 2, or well, it would be like 1.99, which you could round up to 2. If you end up with a number that's not very, very close to a whole number, it means you have one last step remaining. So the ratio here is 1 to 2.5, but you can't have half of a molecule. So that means the true empirical formula has an odd and an even number. So we need to double both of them in order to account for the fact that we need whole numbers and we need them to be the lowest possible ratio. And that would be the final answer. Another version of these questions is the exact same math, but it can be presented in a different way. We've talked about mass spectrometers before. You take a substance and you put it in this machine. It separates the parts by mass and it counts how many of them there are. So the real information that you get out of there is usually based on a percentage. So if we took ibuprofen and put it in a mass spec, what it would tell you is that there's this much carbon, this much hydrogen, and this much oxygen. Okay, it doesn't really matter exactly how many grams there are, because if you know percentages, then you can just assume that you have 100 grams of the substance and turn that percent sign into grams. So regardless of whether the question already starts you with grams or it gives you percentage, you're really looking at grams either way. And our first step is always convert it to moles, because we need to get away from mass. So 12.01 And what we end up with here is not the lowest whole number ratio, but we now have a ratio of carbon to hydrogen to oxygen. The next step, in order to try to work our way towards actual whole numbers, divide by the smallest one. This is what the calculator will tell you. Okay, so this is a really good example of one number where you're allowed to round to a whole number and another one where you can't. So really we're looking at this being 9. So these two have already, H and O have already been reduced to a whole number, but 6.5 is really kind of stuck. So the only way to make that work is you're going to have to double all of them. So the true formula should be C13, H18, O2. The final step in any of these is if you can take your empirical formula and actually figure out the final identity of the substance. Sometimes the empirical formula is the final identity. So for example, with the ibuprofen, because this is a mixture of odd and even numbers, it's probably already the molecular formula. But if you have all even numbers or something that can reduce very low, you might have to do this extra step. So, and the only way to do this is if you are told what the molecular mass is. So here we have C2H3O. That's the empirical formula. If you add up what the molar mass of the empirical formula is, it is not equal to what we know the molecular formula should weigh. It only weighs 43.05 grams per mole. Alright, so already by looking at this, you can probably tell what the issue is here. The molecular formula is supposed to weigh 86. This only weighs 43. So that means that the empirical formula has been reduced by a factor of 2. So the molecular formula is C4H6O2. If you're given all of the information at one time, it's usually written in this version. So it'll tell you what the molar mass is, and it'll tell you what the breakdown of the substance is. In order to work your way from the breakdown to the final formula, you've got to start with turning this into grams and then follow all the steps. Get to empirical formula, then compare the mass of the empirical formula to 60 and see if it's right or how much it's been reduced by. Following the first step, we're going to end up with this unreduced empirical formula. So the next step is going to be divide those three by the smallest one to see if we can get whole numbers. And luckily for us, all three of them work out to be extremely close to a whole number, which means that you can just round, so we don't have to do any extra work. So the empirical formula of whatever substance this is CH4N. Okay, the empirical mass, you have to add up the carbon plus the hydrogen plus the nitrogen is 30. Okay, so the empirical mass is only 30 if we add these parts together. It told us that the molecular mass was supposed to be 60. So that means this empirical formula has been reduced by a factor of 2. So the final answer is C2H8N2. That's the real identity of whatever this substance is. Empirical formula can also be useful for figuring out what the X and Y are of a hydrocarbon in combustion. And the reason is if you know the mass of carbon dioxide and water produced, okay, all of the carbon in the carbon dioxide could only have come from here. And all of the hydrogen in water was located here before the combustion happened. So instead of taking carbon, just carbon directly related to carbon, carbon dioxide directly relates to carbon because it's the only place that the carbon could have come from. The hydrogen in the water is the only place that the hydrogen could have come from was where it was originally attached on the CXHY. Let me explain how this works. So, kind of written similar, except instead of by element, it's by carbon dioxide and water, which means, okay, we're going to be starting the exact same way, except you're going to use the molar mass of CO2 instead of using the molar mass of just carbon. So using the same step that we used when we had it actually broken down by element, okay, we took the grams of carbon dioxide, the grams of water, divided by the molar mass of the whole substance instead of just one element at a time. And now we know this is how many moles of carbon dioxide we have, and this is how many moles of water we have. And we're going to use that information to break it down into carbon and hydrogen separately. in order to figure out what is the actual number for X and Y. Okay, we know that we have this many moles of carbon dioxide, and the ratio of carbon dioxide to carbon is 1 to 1. So for every carbon dioxide molecule, there is only one carbon, which means that we also have 0.0416 moles of carbon. Okay, hydrogen is a little bit different because for every one water molecule, we have two hydrogens. So if we have 0.05 moles of water, we really have 0.100 moles of H. So this is now the step where we can actually take the moles and divide by the smallest one. So we've essentially gotten to the point where we know that this is the empirical formula for our substance. It's just not actually in the lowest number. If you divide by the smallest one to try to get to whole numbers, hopefully it works out. So close. Okay, well, it almost worked out. So we ended up with one carbon, and for every one carbon, there are 2.4 hydrogens. Okay, not close enough for us to round down to 2. Okay, but it's also not 2.5, so it's not easy enough for us to just double it to get whole numbers. The smallest multiple that will work here is 5. Okay, so if we multiply both of these numbers by 5, we'll end up with nice, neat whole numbers, C5H12. So that means originally our combustion was C5H12 plus oxygen. And based on the amount of carbon dioxide and water produced, we were able to figure out how much carbon, how much hydrogen was in the original substance.